Let's do that again. I was muted. All right. Good morning, everyone. Let's get started with today's exercise. So we last class we did the wrangling of the yield monitor data, which was just a very light wrangling that was not related to yield editor or yield data cleaning. I have those two separate steps here because yield data cleaning itself, even though it is mostly going to be related to wrangling, but it is a very special type of wrangling that we apply to yield monitor data. And because of that, we kept it separate. So last class, we did a little bit of the wrangling to begin with, and now we're going to actually get into the yield editor steps or filters that you got familiar with when you read the paper. So what I want to ask you to do is to launch your R project for the 07 yield monitor that we created for the previous exercise. So we're keeping the same project, not creating a new one. You can just launch that. I believe I asked you all to already pull or download the GitHub repo last time. So you feel free to correct me if I'm wrong, but I believe that you already brought in the script that is called 0212 yield editor partial. I think you should already have that, right? So that's the one that we're going to be working on today. So once you launched, so always make sure you are in the right project. So you save yourself hassle when importing and exporting files. Once you're in the right project, you can go on the Files tab. If you're not seeing the code folder, you can click on that R blue button, go to the code folder and launch the yield editor partial script that you have on your side. That's what we're going to be working today. And also, I know I've been using this a lot, but maybe I have not emphasized enough is because we're using the structure here of when we're outside of the chunks, I use a heading 1 level or a heading 2 level with the hashtag number of hashtags in the beginning of the sentence. I create this outline on the right side. And also, if I give my chunks a title or a name, that chunk name is going to appear here as well. So that may help you to navigate your script, especially as we start developing scripts that are a bit larger and more complex. So to see the outline, you just click on that button there. That helps you to navigate. All right.
Question.
Someone online has a question?
Yep. Question. I launched the 0212, the editor partial, that one, I had opened it on the 09, and then there's two tabs open up at the top. Could I close out the 09 and still work this one without issues, or would I need to leave the first one open?
No, you can close the other one. So you're saying like you have the yield wrangling partial open up?
I'm assuming that's what it is. It's Clint and Tipton. I had to delete the last half of the name off of it so that my computer would actually run it and show the map.
Yeah.
On everything.
Yeah, no, you're welcome to close that because if you, and I can just do a quick recap here just so we can make that point as well. So on the script from 0209, when we did the wrangling, we brought in the completely like unprocessed CSV. And remember, it was a CSV at that point, so it was not a geospatial file. Then we brought that in, we transformed that to an SF object, which is a geospatial vector type of file or type of object in R, not a file yet. And then in the end of this script here, we actually exported that initially wrangled yield data as a GeoJSON, right? So this, I want to make this point here because I think this can be useful for you as you navigate your own research as well. In the beginning, I used to like have a script where I would do all the wrangling and then get right into the next steps, which normally are more analysis oriented. I decided that it's easier to segment things a little bit more. So I have one script that I bring in raw data, do all the wrangling needed, and then I export the wrangled version to file. And then this version that we exported using the wrangling script from 0209. So this file that we actually exported is what we're going to be importing in our next script. So we kind of keep separate, like a script to process raw data, and then a script to actually analyze the process data. And we export that process data from the first script so we can access that later. So this is something I would recommend that you do, and that is what we're doing here. And because of that, because we did export that file at the end of the 0209 exercise, we do not need to have the 0209 today. We can just close it. And if in your project you had variables here, we didn't even need to have those variables here to begin what we're doing today. All right.
Hello.
Yes.
I just wanted to tell you that Rolando told me that he's a bit busy in field. There was sudden emergency and that's why he is not attending the class.
Sounds good. No worries. Thanks, Kumar, for the heads up. Okay, so let's get started with today's exercise. So today, my learning objectives for you is that we're going to learn and actually implement some of the monitor data cleaning steps that you read on the paper. We're not going to be implementing all of them, but we're going to be implementing some of them, and I want to show you how we do that. And as we are filtering this EO data set and removing points that we may consider erroneous, we're going to be creating tables to compare the summary statistics, both numerically through tables, but also through maps. So we're going to be making maps and seeing where in the field we're actually removing those points and what's going on there. All right, so the first chunk here is just some packages. What I would say is you probably, I don't think you have LeafSync yet, so I left that for you there to install. So, you know, what you could do here is just uncomment that install packages, run only that line of code, not the whole chunk. And once it installs, you comment it off or delete that from your script so it doesn't interfere with future runs. And same thing for patchwork. And just a quick, as you're doing that, I just want to tell you a little bit more about these two packages. So LeafSync is a package that's going to help us to have two map views side by side, and they're synced. So you can have one with the raw data, one with the filter data, and you can zoom in, zoom out, go to specific points simultaneously in both maps. So that just helped us to do that. And then Patchwork is a package that helps us to combine multiple ggplot objects into the same plot. I think you've seen this already, probably already have this because we used this in the previous exercise of the open source data. So maybe you already have this, but yeah, I don't think you have LeafSync. So please go ahead and install if needed. And once you have it all installed, make sure again that you comment off or that you delete those installed packages lines of code, and then feel free to just run the whole chunk. So we would, so you just load the packages. One thing that, so as you're, so today is the deadline for you to submit your mini project, I believe. And just again, whenever you load your packages on that mini project, if you want to inhibit messages from some of the packages, for example, if we're doing tidyverse that always has some messages to come through, you can do that a couple different ways. One of them is by changing this chunk option here, message, colon, and then set that to false. That's one way. There's also another argument that is warning that you can set to false. And these things will inhibit some of that. Yep.
I have one question. The first question on there. I was doing it, I originally put. It was showing that, or asking what the minimum and maximum values for the year was. And was that you asking which year had the lowest value, or what the, like, I guess the latest year we got that in the earliest year?
I mean, I have to, do you have the question in front of you there?
I forget.
just so we can look. So I know that there's some questions I'm asking, what's the, like, what is the actual year that you have data for? So like if 2023 is the last year that was reported, that would be your answer. But then, of course, you answer that by running the functions to check.
Yes, it was. What were the minimum and maximum years reported on your data?
Yeah,
So
so
that would be like. Okay, so that's, you're not looking for the 5 months acres harvested, you're not looking for the least amount of acres harvested.
yeah.
Most for that.
Yeah, so I'm really looking to know, like, is like 2020, like from 1980 to 2023. That's what I'm looking for in that question. Yeah. All right. Okay, so maybe I don't think we're gonna be able to finish this exercise today. It's a longer script, even though we have 2 hours. So maybe we can save the last 15 minutes or so in case anyone has any mini project questions. We can go over that. So yeah, maybe we can do that. All right, so coming back to the script here. So always, the first step here is to import data. I left you the object name that I want to, I guess, assign this data to. So let's go ahead, give it the assignment symbol. We're gonna use a function readsf. And the reason for this is, if you remember on the previous script, we had a CSV file. So we used read CSV. We brought that in, we wrangled a little bit, transform it to SF object, export it as a GeoJSON. Now we're reading a GeoJSON file. So read CSV does not work with that. We have to use read SF. So we use read SF, open and close quotation marks. Let's navigate to your data folder. So .. hit tab, select data. And then you should have now, on your side, you have just the yield 17 processed. I have already the end product of this script here, which is the clean, but you have the processed, and that's what we want to bring in. So run that, you should see this in your environment. If you just print it, it should have, 31, almost 32,000 rows and 4 columns, 4 fields. It should be of a geometry type of type point. So this is, again, is useful. If you make a map, you will be able to see this, but if you're just bringing, a shape file that somebody sends you, sometimes you may ask them for a boundary and then you import it and it's a point. So you can be sure that that person maybe did not send you the correct one, just by looking at the type here. So it is a point, it makes sense. This is yield monitor data. And also it is coming already with a projected CRS. If you remember, this is a GeoJSON file where that CRS information is already embedded in the single file. If you had a shape file instead, this information would be included in the PRJ accompanying file, I guess, of the SHP file. So another reason, again, why we use GeoJSON is because everything is a single file, so it's easier to share, I guess. And then if you come on the second pane here, we see that we already have those wrangled columns. So we just kept the ones we wanted, which was speed in English and in international units, and metric system units, and also yield both in those systems as well. And then we also had the geometry here, because that's what makes an SF object, is that having that geometry there to carry that spatial information. All right, so we're just going to do a quick summary here. This we have already seen at the summary of this data on the previous exercise. We see that there are some yield values here that are very high, that are most likely not correct. Okay, next step here that I want to do is a yield map, a static yield map using ggplot, and I want to plot the raw data, and I do want to assign this ggplot to an object called EOMAP_raw, right? So the reason why I want to do that is because in the end, I want to call this map again, and instead of just retyping the whole thing, we can just call the object name. So if we get started here, I left you the first part of that plot, which is just the ggplot and the object name. You can add a plus there, hit return. Now, this is an SF object Because of that, we need to use GeoMSF. So we call GeoMSF here. The data is already specified at a ggplot level, so we can leave that empty. We can get right straight into the AES. And I just want to do one thing here, which is I want to color the points based on the yield pound per acre column. So that is called yield underscore LBAC. If we run that, I do want to take just a quick moment here to remind you of something. So if you are creating a plot, or even that doesn't have to be a plot, if you're creating anything and assigning that whatever it is to an object, and you run that, that's not going to show you the actual output, right? If you want to print what's in it, you have to call that object name, so you see, so it actually prints that object for you. So that's what we're doing here. So we assign that and then we print it. So this is how it looks like. Because it is an SF object and we're using GeoMSF, it already sets the X and Y axis scales to be what it would be in space. So it looks like the field that we're working with. I want to change two very quick things here. So one of them is still inside of this GeoMSF. I just want to change the size of the points. So you go outside of the AES. Remember, we use the AES when we want to assign something like color, shape, fill, whatever it is, to a column. In this case here, we did with the yield pounds per acre. But if I want to change any of those aesthetics on a fixed value for all points, I do that outside of the AES. So I want to change size to be equals to 0.1, just to make these points a little bit smaller and have less overlap. And also I want to change the color scale here, right? Now, I do want to emphasize this again because, you know, we're doing this together here and perhaps you're not realizing fully what you're typing. So to change the color scale in this case, I need to use a function called scale underscore. In this case, it has to be scale underscore color because that's what I'm changing the AES. If I do scale fill, it's not going to work. It has to be color. And I do want to use the Viridis B for bind. So remember that with continuous data like yield is, we could use the Viridis C, which is for continuous data, or the Viridis B. If we use, I'm going to use the B on my side just to make bins, because I think it's a little bit easier to see some of the patterns. But you could have used also the C for continuous. So the B for bind creates these bins that in this case are at every 1,000 points. If we use the C, there would not be bins. There would actually be a full continuous gradient there. Just so you're aware. I want to propose we keep the B, but at least we can understand the difference there. All right, so we created this quick map of the raw data. We assigned that to an object, and we're visualizing this. As we already saw before, we have lower yields in these eroded sides of the field, and also some of the boundaries as well. Okay, so next thing is I want to do an interactive map here with us. I left you part of the code, and if you just run this, it's gonna give you errors because I have used, you know, some ways of hiding the code, or not hiding, but not providing you the code that are not our language per se. So it's gonna give you an error. But just to walk you through what we already have. So we're starting with yield 17W, so that's our SF object. We are filtering to only keep the points of yield that are below 3,000 pounds per acre. Then we're calling a pipe and sending that right into a map view, where I'm saying that I want to color the points according to that yield pounds per acre. I'm providing this Viridis 3 is basically creating a color scheme of 3 levels for our regions. In this case, the regions are whatever we're coloring here. So that's the yield pounds per acre. I'm making them solid, so no transparency, changing the point size to 0.1. And then there's 2 more things I want to do here in my code. So if you add a comma there, and then you come to the line below, remove those 3 dots. That is not our code. That's not gonna work if you leave them. I want to change the width of the points. So we do that by doing LWD is the name of this argument for line width. I want to do a line width of 0. So have no outline on the points. And then lastly, we talked a little bit about this before, is if we just run this map here, if you recall, map view gives you the base map by default that is not the satellite imagery. And I do want to have the satellite imagery. So to change that, you can come here in the next one. Let's do map.types. And the name that we need for the satellite imagery here in quotation marks is Esri with E uppercase, dot world with the W uppercase, imagery with the I uppercase. So this is what we need to have the default base map to be that satellite imagery. So once you run this, if you were able to not have any issues, if you're having issues in your code, make sure you remove the dots that I left you in the beginning. Make sure you have your commas at the end of each one of those arguments. Make sure that you correctly spelled Esri world imagery as it is in my case here. And again, when you do that, you're going to realize that this is going to be assigned to an object. So for you to actually see what's going on, you have to print that object, which I left you the code there. So this is what we're seeing of this interactive map. Right, so you can zoom in, zoom out, we can really see, and we already played a little bit of this on the previous exercise, but I just want to have this object here, or this map view interactive plot assigned to an object so we can call this later in the script. Okay, so today I want to propose that we apply 5 of the filters that you read. I think the paper had like, I don't remember the number now, something like 12 or 14, 15 filters. We're going to be applying 5 of them here that are going to be the minimum and maximum yields, the minimum and maximum speed, and also the position filter.
I got an error trying to do the interactive map.
Did it give you a message that perhaps can help us troubleshoot?
It said error in normalized path. And yeah, like it ran the code fine. It was just when I went to print the interactive map was when it gave an error.
So when you print it, does it still show you the map or does it not even show it?
So just an error.
Okay. Let's see if let me try something here on my side. Okay, so maybe we can try, if you try to just comment off that call regions and try to run again and see if that works.
It's still running.
Okay. While we wait, did anyone else have issues creating the map?
Yeah, I got the same thing.
Okay. So I'm not sure why. Maybe for now, let's pin that for later, and then maybe we can connect after class today or some other time to troubleshoot it on via Zoom 101.
Okay, I can do that. I was gonna say I was just zooming into class where I can share my screen, but I can meet up with you later. if that works.
Yeah, I think especially since it seems like no one else was having the same issue, maybe if we, because I don't think it's gonna impact your exercise today. But we definitely want to get this fixed, you know, at least before we reach the end of this script, but I don't think we're gonna be able to reach the end by today anyways.
Okay,
I had some corrections to the name file.
Okay,
They should
it could be, so, and that was Clint in Athens, in Tifton?
yes, sir.
Yeah, so Clint, so Neva here in Athens was saying that she had a similar issue and then the fix was just decreasing the file name's length. Did you try doing that for this script?
I will try that.
So what I would say is make sure you click on the save button on your script so you don't lose what you already did. And then I would recommend that you close the script here before renaming. So you can close here.
Okay.
And then rename, yeah.
close the,
Okay,
you can just rename from the.
Oh, really? Okay, so Neva is saying we can actually rename right from there. Let me open that up here again. I know we can, so I usually rename either on my file system as I would rename any other file or through here. Is that what you're saying, Neva? Yeah, okay, so yeah, if you were to just select that file, the editor partial, and click on that button right there, you can rename it. And Neva is saying that you may not even need to close it. So, you know, you can just rename it and then try to run it again. Maybe that would be the fix.
yeah, that got it.
Okay, did it work?
Yes, sir.
All right. Yeah, so it seems like the fact of, you know, the file length or the file name being too lengthy, it is interacting with Windows systems and it's having issues there. So that seems like it's probably the go-to solution if anyone has any type of issues like that, and if you're using Windows. All right, so I left you, so what I want to do first here, and I do want to emphasize this, I try to emphasize this as much as I can. Regardless of what you're doing, whatever data it is, always make plots to visualize your data. That's the best way for you to create understanding of what's going on. So the first thing I want to do here is look at the raw yield distribution. I left you the code already there, so you can just go ahead and run it. We already made this plot on the previous exercise. I just want to bring this up for us to look at it again. It looks like the peak of this distribution, which would be the mean of that, is probably around, you know, 1400 perhaps for this side here. We see there's a larger number of zeros, so or very close to zero yield in this tail here, right? So if this was a normal distribution, you would not have such a high tail on the lower end. We do have a lot of lower yielding points. That could be actual low yielding points, could also be erroneous data points because of the way the data is collected. And then we see that the majority of points are probably within, I don't know, perhaps the maximum that I'm showing here is probably like 2500. But then we have maybe 5 points that extend all the way, that make this tail, this distribution very long to the right. So it's really very much possible that those points are erroneous data points that we have to clean out. All right, so if we come to the next chunk, I just want to get now a statistical summary of just the yield data. We can use the summary function that we've been using already. If you just give the object name yield 17_W, you're going to get a summary for all columns. If I want to focus just in one column, I can come here, add the $, so it gives me the option of selecting just a column, and then we can select just that yield pound per acre if I only want to look at that summary. So here we are now with numbers, we confirm what we were seeing on the plots with our minimum being 0, maximum being over 4,000 pounds per acre. And then our first quantile, median, mean, third quantile distribution. So just putting numbers to what we visually saw here on this plot. Okay, so based on the paper, oh yeah, go ahead, Doug.
Your unexpected input for summary 17.
You made, did you have the object name typed correctly? So the yield 17W? And then you're using the dollar sign after it and giving the column name?
Again,
Okay. Was that a typo in the name?
it was a typo in the dollar sign for some reason.
Okay, yep. Awesome. All right, so the first thing here that I want to do is filter based on yield. If you remember from the paper you read, the way that the paper proposes to do this is basically using the data distribution itself, right? So it's not going to come here and just assign a fixed limit of lower boundary, upper boundary. It's actually going to use the data itself to determine those boundaries based on the data distribution. So if you recall there are a few things here that we're going to be calculating or extracting from this distribution here. And I'm calling them low Q yield, upper Q yield. So these are for the quantiles. Then we're going to get the inner quantile range. And then finally the minimum Y and the max Y, which are going to be based on those numbers. So this is exactly how it was described in that paper. We're just going to implement those here in R. So to determine our lower quantile that we want to, so we want to determine a lower, somewhere in this lower side, or this left side of this distribution, we're going to determine the lower quantile here. That is actually based on the paper is the 10th quantile. So if you think of quantiles, is basically, if you take all of your data and you rank it from lowest to highest, the quantile is basically the position within that distribution. So we're going to take the 10th, so if you have a scale of 100, we're going to take the 10th % position in the distribution, and that's going to be your 10th quantile. To do that in R, let's get started with the coding here on the low Q yield. R has a function called quantile that we can just give what is the variable that we want to get the quantile of. So that variable is the yield. So we first call the object name, yield 17W, use the dollar sign, and call just the yield pound per acre, because that's the column we want to get the quantile of. And then the next argument here is the actual quantile that goes from 0 to 1. So 0 would be the 0th quantile, 1 would be the 100th quantile. So I wanted the 10th quantile, so I need to say 0.1. So if you run that and you print it, you should get that the 10th quantile is the yield value of 551 pounds per acre. That's our 10th quantile of that distribution up here. We're going to do the same for the upper quantile. So give the assignment symbol. We're going to call the quantile function again. We're going to give the same object as far as yield 17 underscore W, dollar sign, yield pound per acre, still the same column that we want the quantile of. And the paper proposed that we use an upper quantile of 99. So 99th quantile, we need to type 0.99. If you run that and you print that UPQ yield, you get a value of 1939.48. So this is the yield value in pounds per acre that represents the 99th quantile of the distribution above. Now we're going to use basically the upper quantile and the lower quantile to determine the inner quantile range. This is again something that the paper has formulas. You can go back to it and refer to it. And if you don't remember what that means, but basically the inner quantile range is just the upper quantile yield. I'm just going to copy that object name minus the low quantile yield. So if you run this and you print it, now you get this difference here between the upper threshold and the lower threshold, that the difference between them is 1388.056. So this is the, if you think about it, it's how much distance you have from the low quantile to the upper quantile. Then the paper that proposes that instead of just using those limits, the low quantile and upper quantile limits. So imagine if you think about it, low quantile is 551, upper quantile is 1939. Instead of using those limits and filtering everything outside of it, it actually extends those limits a little bit. It calls that min y when we extend on the minimum side and max y when we extend outwards on the max side. So that's what we're going to do next here. On the min y, the formula, again, coming from the paper, is going to be the low Q yield, so the low quantile yield minus the inner quantile range, so IQR, which is the object that we created above, times 0.25. So it is taking the inner quantile range, that is like 1300 and something, and taking 25% of it, and then deducting this amount from the low quantile. So if I just run IQR times 0.25, that gives me 347 pounds per acre. So I'm making the low Q yield minus the 300 and something. So I'm making my min Y go even more to the left on that distribution than my low quantile. So now my minimum Y is 204 pounds. So again, low quantile yields based on the quantile, 10th quantile was 551. I'm making this limit go even further closer to zero by deducting the 25% of the inner quantile range. And I'm calling that min Y. So min Y is 204 pounds per acre. Now we're going to do the same thing on the max Y, but instead of deducting, we're going to be adding because we want to extend past it because it is on the upper side of that distribution. So we can come here. It's going to be the upper quantile yield plus, so not less, but plus the inner quantile range, IQR times 0.25. So if we do that and we print max Y, we see the max Y becomes 2,286, whereas our upper quantile yield was 1939. So we basically extended that upper quantile a little bit more, taking into account 25% of the inner quantile range. Okay, so we did all these numerical assessments, and now I do want to take the time for us to think through of how to visualize what's going on, what we're doing to this data, right? Because we're using all these formulas, and sometimes it may be difficult to visualize what's actually happening if you're just looking at these numbers. So let's create a plot with that. So what I want to do here, if you just run the piece of code that I left you, it's just that distribution again. What I do want to do now is basically show you exactly creating vertical lines on this plot, where those limits are, and then we can understand what we're keeping in, what we're removing on this step here of the min and max yield. All right, so if you come right after the code that I left you there, the first thing that I want to add is I want to add a vertical line right where the low quantile yield threshold is. So let's come here at a plus. I don't remember now if in this class we already talked about it, but there are two geoms that we can use to add lines in a given place. If I want to add a line on the x-axis, I use geom v line for vertical line. If I want to add a line on the y-axis, I add a geom h line for horizontal. So in this case, geom v line, we're not giving it a data set itself. It's just going to be a value. So we're not going to use AES. Here it has this argument called x-intercept. So it's basically the value on the x-axis that you want to create a vertical line. This value here is the low Q underscore yield. So it's whatever value was assigned to that object is what I want to have here. So if you run this is what you should get. I do want to just change a few things here to make it easier for us to visualize. So the first thing is, if you go back to that geom v line, add a comma, I want to change the color equals red. And it has an argument called line type. I want to say line type equals to 2. So if you run that, you should be seeing this vertical line that it starts at low Q yield and cuts through the entire y-axis. That is colored line and it has a dashed line type. Okay, so next I wanna, you can either copy this that we just did, so just the GeoMV line, or you can type it out again if you wish. But if you just copy what we did here, add a plus, hit return and paste. The next thing I want to do is add a blue line on the upper quantile. So the two things we have to change is instead of the low Q, it has to be the high Q. I think that's how it's named. Let's see. No, not high, up. Check my object name, I'm forgetting. Yeah, the UPQ yield is the object that we want to change here on the x-intercepts. And instead of coloring red, I just want to color it blue. And also have a line type equals to 2. So if you run that, now you have this dashed blue line that is at the upper quantile yield value. If anyone has any issues here with the code that you cannot figure out, please let me know. If I don't hear anything, I'm just going to keep moving. All right, so the next thing that I want to do here is add another vertical line on the mean y value. So remember, the mean y is going to be to the left of the low Q value. So what I want to propose, I mean, maybe here we can just type the whole thing because we're going to be changing basically everything. So if you just add a plus, hit return, let's bring the GeoMV line again. I want my x-intercept to be equals to my min y object. I give it a comma. I want the color of that to be equals to red. And I want the line type to be equals to 1. That is a solid line instead of a dash line. If you run that successfully, this is what you should be seeing. So a solid red line at min y. For that, you change the color, you change line type to 1, and the x-intercept is the min y object. The next thing I want to do here is do the same but for max y. So maybe if you want to copy here, you can copy the last one we did, add a plus, paste that, make sure to change your x-intercept to max y. And I also want to color that blue instead of red. And I want a line type of 1. So just change your max y and color to blue, keep the line type equals to 1. If you run that, this is what we get. And then lastly, I just want to fill in the space here that we're going to keep. So if you remember from the paper, they find the quantiles first, which are the dashed lines here. They extend those quantiles using the inner quantile range times 25. In this case, creating the min y and max y, which are the solid lines. And then they keep only the data within the solid lines. So basically, you exclude everything outside of the solid lines right there, based on this filter. So I do want to show you here visually what would be this space here within the solid lines. So if you add a plus there, we're gonna introduce you to a new function, I guess, that we have not used yet. It's called annotate, with ANN, annotate, where we're going to provide here a list of arguments. The first one is I want to create a rectangle within that space. So I need to say that the geom I want to annotate is going to be equals to rect within quotation marks, short for rectangle. I need to give it the dimensions of where things are starting and ending. So my y minimum, I'm setting to 0. So imagine that I wanna basically have a rectangle showing everything inside of this box within the solid lines. So on the y-axis, it starts at 0. And then the y max, so the maximum value on the y-axis is actually the maximum value that we have here. So we could either provide the maximum value of the density, which is not very easy for us to see, or we can just provide uppercase I inf for infinity. So basically it's gonna keep going to infinity, but in our case, it's gonna stop wherever the plot, the data range in this plot ends. So that's an easy way to do that. So we don't have to get exactly the maximum value on the y-axis. We're gonna do the same for the x-axis, so determining where I want my rectangle to start and end. So the x min is gonna be the value on the x-axis where I want the rectangle to start. What should x min be? We have an object that is exactly that value on the x-axis. What is the object name that has the value on the x-axis that I want to start this rectangle? If I want to go from the solid line, the red solid line to the blue solid line. So min y, right? So the x min here we can just call min y. That is the actual value that we used that vertical line at. And then you can give it a comma. We call x max is going to be the maximum value. That's going to be similarly our max y. If we run this, I think it would already work. So we can just run and see what happens. Yeah. So it already worked, already created this rectangle to be within that space. However, we want to do 2 more tweaks here. One of them is going to be to change the argument alpha for transparency. So when I have an alpha less than 1, 1 is completely solid like we're seeing here. I want to say alpha equals to 0.6 to give it a 60% transparency so we can see through it. And then finally, I just want to change the fill. So I want to call fill equals to, open and close quotation marks, green, or a green color. To indicate that we are keeping everything within the green rectangle here. So again, this is just a visual way for us to understand what is actually happening with the algorithm and what data we're actually keeping, which, you know, I guess perhaps just by looking at these numbers, maybe you already created some of that understanding, but I think that really making a plot to visualize what those limits are, how they relate to one another, and what you're actually keeping help us to create this understanding, right? So we're basically any data points that are outside of this green area are going to be removed at this filter, which is the min and max yield filter. And again, this plot here did not filter anything. It was just visualizing, right? So this did not, there is no data wrangling here. There was no new object creation here. It was just for visualization purposes. So now let's actually implement what this filter is actually doing. So if you come here, I'm calling this object EO17WYF for yield filter. That's going to be our initial object of EO17W. And now we can actually do the filter. I do want to ask you all to help me here because I am very confident that you can think about how this would happen on your side without me having to give you the answer right away. So if you were to keep or if we were to use a pipe there, let's begin with the function. What function would you use to apply this filter? Think about the data wrangling functions we've been using whenever we want to do something similar or we did in the past. What function did we use for that?
Dplyr select.
Okay, so
Dplyr.
So dplyr select is a function that we use when we want to select certain columns, right? So in this case here, we want to, I guess, select certain rows instead. What do we use for rows? Filter, right? Yes. So we use the function filter. And now I just want to print EO17W here, just so we can see we can look at the column names here. We've been using the column yield pounds per acre. So that was the one that we used to determine the quantiles. So we do want to filter based on that. If we had determined the quantiles based on yield kilograms per hectare, then we would filter based on the kilograms per hectare column. But we did base ours on the yield pounds per acre, so we're gonna use that to filter. Okay, so we're using the filter function. So, and this is a good time to remember. Select is to select columns. Filter, we use to select rows, right? So we want to only keep the rows that fulfill a certain condition that we're going to specify here. All right, so again, if I'm gonna tell you in words, and I wanted to help me to determine the code to implement that. If I want to keep all values that are within this green rectangle here, and we know where this rectangle begins and ends, how can you translate that to code right here? Renelisa, what do you think? Oh,
So what was your question again?
so you having trouble with the plot?
No.
I cannot quite see from here. Is that on the annotate?
The filter. So in the filter function.
Right here?
Yes.
Well, I mean, if you're just running this, it's gonna give you an error because we have not typed in what we need. Yeah. But so, you know, how would you apply this understanding here that you want to keep values between this point and this point in a filter function?
Can we use concatenate function to like to put a value minimum to maximum from y
So,
min to y max?
okay, so you're thinking the right direction. I don't think we need a concatenate function, at least not the way that I'm thinking.
Okay.
But okay, Kumar, so tell me this. What would be the first way or first condition that you would write in code?
If it is within these two ends, I think whatever I'll want to write on the code, that should denote that my data is supposed to be between these two lines.
Okay. All right, so let me help you out with the first part of this, and then you can help me out with the second. So if I want to keep, so really translating this more into a Boolean type of logic, I guess, I want to keep points that are greater than min y, but also lower than max y,
Lower than max y.
right? Because if I only say more greater than min y, it's going to keep everything, including this large thing on the
Yeah.
right. So I want to create a lower and an upper boundary of my filter condition, right? So come here, I would say I want to keep yield pounds per acre that is greater than min y. But for me to give it the upper boundary as well, I want to say and. So the point has to fulfill both conditions to be kept. So it has to be greater than min y, and at the same time, yield pounds per acre has to be lower than max y. Right? So if a point is greater than min y, but it is also greater than max y, it's not going to be in the data set. It's going to be left out because it does not fulfill both conditions. It has to fulfill both conditions for it to be kept in the data set. And this is it. That's what we do to apply the min max yield filter. So it's really simple implementation, even though it may sound more complicated. Okay, so before we apply this filter here, we had 31,724 rows. And now you can see here that we have about 30,385. So we reduced around, 1,200 rows, something like that, or 1,500 rows actually. 400. Anyways, over 1,000 rows of data we kept out, which were all the points that were outside of those two boundaries in this plot. All right, so now that we apply this filter, I do want to get a summary of the yield data points that were left in the data set, just like we did before with the raw data, but now with this filter based on yield. So we're going to use the summary function, oops, not summarize, summary. And now we're going to call this object that we just created, because this is the one that has the actual filter data points. So that's called yield 17 WYF. And then I just want to get a summary of the yield pounds per acre column. So I use a $ and call just that column. So now when we do a summary here, we can confirm that our minimum now is 204, which is very close to the min Y threshold. Our maximum is 2,282, which is also really close to the max Y threshold. And if you stay here, so you don't have to move as I'm going to, but if you stay here and we go to the, let's see, the summary right here. Wait, I think we had maybe a chunk where I just showed the summary. Oh, okay, right here. So this is the summary of before we apply this min max yield filter. We see the minimum was 0, the maximum was 4,000 something, and also the quantiles were probably a little bit different than what they are now. So we applied the min max filter, and then we got this new statistical summary that you're seeing on your side with the minimum of 204, maximum 2,282, and so on. Okay, so we basically just implemented this filter based on min and max yield values. Now, the next one that we're going to do is a very similar one, but instead of looking at yield, we're going to look at speed, right? So that was the other two set of filters that you read in the paper. I left you the code again here for us to just look at the distribution of speed. We see that speed in miles per hour were most of the time around, this is probably 4.7 miles per hour. We had a little bit of data around it as well. And then we have some long tails, especially to the left, where the combine was moving very slowly. And we know that when it is moving very slowly, we can have these erroneous data points. So, so we just saw this, in a plot. Now I want to come here and actually get a statistical summary in a table format. We see the minimum speed was 1, maximum was 5. Mean and median were around 4.7. So just creating some of that understanding of this distribution that we saw as a plot, and now looking at a statistical summary. And I left you here. So basically, if you remember from the paper, the way that the speed filters were determined were very similar to how the yield was determined, as far as using quantiles and then expanding those quantiles outwards and keeping, that type of data. So that's what we want to do here, is just repeat those steps. You're going to have to help to develop the code of the low Q speed and upper Q speed, but then after that, I left it for you already. So low Q speed, we're going to use again that quantile function. Make sure that we call here the yield 17 W $ speed in miles per hour. And then if you recall, one thing that the paper, so these thresholds that we're using are coming from the paper. They propose that for the speed filter, we use a quantile of 8, so the 8th quantile. So that would be 0.08 as the quantile for our low quantile on the speed data. If you recall what we just did above for yield, we used the 10th quantile. So it's a little bit of a different quantile. They don't really explain why they propose different quantiles in the paper, but we're just following what they had there. So using the 8th quantile, you should get a speed of 4.6 miles per hour. Next, we do the same for the upper quantile. So we call the function quantile again. We again call it the yield 17 W $ speed in miles per hour. And for the upper quintile, they're also using the 99th quintile here on the speed. So this one matches the same quintile that we got for the yield one. So if we do the 99th quintile and we print that, we get 4.8. So we see that this data distribution is really tight, right? So the low quintile is 4.6, the upper quintile is 4.8. So really tight distribution here on the speed. I left you the code for the inner quantile range, IQR, so you can just go ahead and run it. The IQR in this case is 0.2. It's just the difference between the 4.8 and 4.6. I left you the code for the mean. I'm calling this mean V now. Before I was calling mean Y for yield. So in this case, mean V is going to be the low quantile speed minus 18% of the inner quantile range. So not a lot. So mean V is going to be then 4.56. Max V is going to be also 18% of the upper quantile range, but adding to it instead of subtracting as we did for mean V. So max V is going to be 4.8. So our thresholds here are going to be mean V, 4.56, and max V, 4.83. Very tight distribution. I left you all the code here because we already developed this code and the intuition for the code for the yield part. I'm just leaving all the code here. Of course, I am changing the variables as far as, I'm using all the quantile for speed and the mean V and max V instead of the ones for yield that we saw for the yield plot. So if you just go ahead and run it, you can really see how tight that distribution is. Even the quantiles and the minimums and the maximums are really close together, and we're only keeping the data points within that green rectangle, right? So everything outside of it, we're keeping, or we're leaving outside. We're leaving out when we do the filter. Okay, so now we basically come here to implement the filter. At this point, so I'm going to assign whatever we do to this object called EO17WSF for a speed filter. I want to begin with the data set that we have already filtered the yield data points. So that is the yield 17 underscore W underscore YF. Make sure you bring YF and not just stopping at yield 17W, since we have already applied a filter to the YF. Add a pipe. So now I'm not gonna help you this time. You're gonna have to help me to develop this code here. So it can be more than one person, doesn't have to be all the same person, but I do want your help. What function do we need? Filter, right? Okay, so Sandesh, what column now should we apply this filter based on? Speed, right? So speed miles per hour, that was the one that we created the quantiles based on. So that's the one that we want to apply the filter to as well. Okay, so what would be the first condition here that you would specify? Greater than minimum V, all right. Pushball, help me out here. What would you do next?
Greater than maximum V.
Okay, so you do speed less than max V. Okay, but there's something missing, right? And yes, we're missing the end here, just to specify that we're keeping rows that fulfill both conditions. If they fulfill just one condition, that's not enough, they've been left out. All right, so if we run this and we run that object, we see now that our number of rows decreased to 28,950. Right, so I just want to print again just the yield 17 WYF, which is the one that we applied the yield, the mean max yield only. So that one had 30,385 rows. Now, after applying the speed filter, we have 28,950. So again, we removed probably around over 1,000 rows In this case, based on the speed filter. All right, so let's take a look at the statistical summary. Yes.
So on the ones before we used min Y and max Y,
Mhm.
what's the difference in the min V and max V? Why are we using V instead of?
Yeah, so that's a good question that I kind of went fast through it. So, you know, this is the code that we are creating the quantiles and IQR and the min and max for speed. Yeah, no, and I didn't, I guess, point that out very clearly, but yeah, so min V is what we're creating here, and max V we're also creating here in this chunk for the speed filters. And the min Y and max Y were at the yield level, right? So these values here are based on a different column, so they should be a different object as well. So we can just, we don't have to overwrite on the same object name. All right, so again, let's get a statistical summary of the speed, or let me see, I'm doing, yeah. So statistical summary of the speed column after we filter on min max speed. So let's call the function summary again. I want to call the object that we just created. So that's yield17 underscore W underscore SF for a speed filter. And if I just want to look at the speed column, you use a $sign. Let's call speed miles per hour. So if you run that, we see now that our minimum is 4.6, our maximum is 4.8, which are within the min V and max V that we determined. All right, so we just finished applying for those filters, mean and max yield, mean and max speed. The next one that I want to show you how to do is the position filter, which is going to bring in some new concepts. I think new concepts. I don't think we saw this yet. So based on the paper, if you recall, we could apply the position filter two ways. Or I guess they provided two options of how to do this. One of them was to use a very similar approach using the distribution of the X and Y coordinates. So you take the X and Y coordinates and apply all the concept that we just applied above and extract a mean X, max X, mean Y, and max Y based on the coordinates of the field. That can be used if you do not have a boundary, right? So we're basically relying on the position in space, getting kind of like that distribution of the coordinates of the points, and using a statistical distribution of those points. So like doing this, but imagine instead of having speed, you have X, or like longitude or latitude and so on. And using that approach, I think that can, I mean, if you don't have a boundary, that works, but we do have a boundary for this field, right? So we all have a boundary for this field, and I want to use that boundary here instead. And just to maybe refresh your head here, so why do we want to use the boundary filter in this case? Is sometimes maybe, you know, we get data from a grower or a collaborator, and they send you yield data, like a shapefile yield monitor data that actually starts collecting data at the shop. So we have all these points coming all the way from the shop to the field, and then you get to the field and you have all the points there, right? So any point that is not within our field does not matter to us, at least not in this exercise. Perhaps if you have multiple fields within the same shapefile, maybe you want to do this analysis on a field by field level, but we're doing for a single field here. So we want to focus on this specific field that we have a boundary for. Also, other cases that can happen is if you have something going on with your GPS. So your GPS, I don't know, maybe you lose signal and then it puts one of your points like in the middle of the trees, or in the middle of a lake going through, or a river going through your property, a stream, whatever that may be. So we want to use this to confine our data just for data that's actually within our boundary. That's the main goal here. So for that, we have to, in this case, since we're going to be using the boundary approach, we have to have a boundary. So let's read that in and assign that to this object called boundary. It is a geospatial vector file, so we need to use readsf. Now, the boundary itself, it's, so at least in my case, okay, we could do two things here. We could either go to our digitizing exercise, copy that boundary we created there, paste it inside of the data folder of this project, and go to this data folder and read that in. That's one option. We could also navigate all the way to that output folder where we did export the boundary and get it straight from that other project, which is what I'm going to propose we do here. So if you open and close quotation marks, we need to get outside a few levels here. So // we get outside of the code folder. We're still inside the EOMonitor project. I want to get outside of this project. // Now I'm seeing all my projects. The boundary is inside of that 05 digitizing. So I go in there, hit tab again. The boundary on my side, I export it into the output folder. I would assume you probably did as well. So we go inside of the output folder, and then you have the boundary.geojson. That's what I want to bring. So again, we're navigating outside of the screen project, go inside of the 05 digitizing project. In there, we go in the output folder and the boundary is there. This is the one that you all digitize on your sides for this field that we're working with. If you do that and you print it, you should have this simple feature object with one feature. It's just one boundary, at least it should be, if you were able to digitize correctly. It is of polygon type because it is a polygon, and it is in WGS 84. If you just want to, let's see here, when we get to that, we're gonna get to plotting it, but if you just wanna make sure that you got the right boundary here, we can just do, you know, a map view. You can do a map view on your boundary just to double check that you got the correct boundary and not perhaps the one for your assignment. So this is the correct boundary for me. I'm just gonna delete that map view from here as that chunk was not intended for this. Okay, I'm gonna take a quick moment here and ask, does anyone need help with this step? All right, I don't hear anything, so I'm assuming you were all able to get the boundary.
Just 1 second.
Yeah.
Just 1 second. I wanted to ask you, you had different number of dots and I have a different number of dots. Is that okay?
Yeah, so
Like,
this is gonna depend on the way that you organize the folders. If you were organizing the
Okay.
folders the way that I was proposing, you should have like the same number of dots. But maybe you didn't, and if that works for you, that's okay. You don't have to be exactly like mine. But as long as you were able to find that boundary.geojson, that's what matters.
Yeah. Okay.
Did you have a question there? All right. Okay, so I'm gonna keep moving here. I want to do a very light wrangling on this boundary. I do want to transform this into UTM. So right now, if we just print that boundary, it's going to be in WGS 84. So it's a geographic coordinate reference system. I do want this to be projected and be in meters instead of angle or degree angles or degree units, I guess. So to do that, let's come to this next chunk. I'm going to give it the assign symbol. We're going to begin with the boundary, and we're going to need a function here. Let me see if somebody can help me to remember. So we have, so this object already has a CRS. We just need to change it to something else. What function do we need for that? Transform, right? ST transform. So let's call ST transform. In here, it has an argument called CRS, and we just give here the EPSG code of the CRS we want to change this into, which is going to be 6345. So if we run that and we print this, now boundary W should have a projected CRS that's NAD 83 UTM zone 16 north. Okay, before we actually move forward with applying this filter, I just want to create a quick plot here. So if you run eomap_raw, this is the object that we assigned that raw data all the way on the top, right? So we already have that. We do not have to type everything again. But I do want to add something to this, which is the boundary, so we can visualize. So if you come here and add a plus, you can kind of think of this eomap underscore raw already being your ggplot, geom, because it is, right? So we can just keep adding as you would any ggplot sequence of functions. So I want to add the boundary here. For that, I want to use geom_sf because the boundary is an SF object. So we say data equals boundary underscore W. That's the object that we just created above. And already here, I want to say fill equals to NA so we can see through it. If you run that and you look, so this, just to make something clear here, I did one last semester, I gave the students the boundary. So everyone had the same boundary. And I noticed that some people did not know how to digitize boundary, which I was assuming everyone knew since, you know, probably you have already taken a precision ag course before this. However, that was not a good assumption on my side because many students did not know how to digitize a boundary. So I included that exercise this year, which means that we all have slightly different boundaries, right? So you may have one that looks a little bit different than mine, and I'm just gonna go with that. I think that that's okay. It's probably, as long as you got the overall shape of the field, you should be okay. But I'm telling you that because from this point on, whenever we use the boundary to do something, all of us are gonna get slightly different results, right? So the number of rows after we apply this filter is gonna be different. Hopefully not by a lot, but by some. And I just wanted to point that out because this is gonna create some differences between us all. Okay, so if I bring in this boundary, you know, here we already knew that we did not have any points outside of the boundary, at least when we looked at the map. However, we do have points that are really close to the boundary that we know can be lower yielding points that we want to remove. So what happens here is I want to remove points that are a certain distance from the boundary. I don't know if you've had something like this in any GIS course that you did before, but this would be called a buffer, right? So we can either create a positive buffer, which is basically from the boundary outwards, or we can create a negative buffer, which is from the boundary inwards. We're going to do the second option, the negative buffer, because we want to remove points that are within a certain distance of the boundary. So if you come here on the next chunk, that's what we're going to do there. I was proposing to use a buffer of 20 meters. I want to show you how we do that, but then I want to talk about it before we move past this chunk here. So to create a buffer, we're going to start with the boundary W. So that's our starting object. We give it a pipe, and there is a function from the SF object called st_buffer. It has this argument called dist for distance. This is where you would say what's the distance that you want to go either outwards or inwards. If I want to go outwards from my boundary, I give a positive number like 20. If I want to go inwards, I just give it a negative number like -20. So I'm going to go with -20 for now. If we now print buffer, this is still a polygon, still just one feature. It's just that whenever we plot this, you're going to see it's going to be bigger than our boundary, or I'm sorry, it's going to be smaller than our boundary in this case because we use a negative buffer. So let's go ahead and plot that so we, again, can have a visual assessment of what's going on. So if you come here, I already left you some of the code. This code, if you run, is going to do the eomap raw and give you the current boundary, which we're seeing there. Now I want to add the buffer to this plot. So add a plus, geom_sf, because we have an SF object. Data equals to the object that we just created that is named buffer. I want to change a couple things here. So one is I want to change the color. I want to say color equals to orange, so we can see better with the background of the plot. And I also want to say fill equals NA, just like we did before, so we can see through it. If you run that, On my side, this is what I get. Again, you may be getting slightly different results because your boundary is different from mine. But I hope, and maybe we can change one more thing here. Let me see, this may be, I'm trying this on the go here. So let's try size equals to 2, see if that works. Okay. Maybe, I don't know if it had any difference. No, so size is not what it need. Maybe it's line. Let me try line width. Yeah, okay. So line width is the argument. Maybe we can have 1.5, just so we can make it a little bit easier to see what is where is the boundary, or where is the buffer in the boundary. Maybe let's also change line width of the boundary itself. So the first UMSF there. So line width equals to 1.5. So just change the line width of both of them so we can make it easier to see. So in this case here, you know, we can see how the negative buffer moved inwards. If this number would have been positive, I just want to change that very quickly so you can see. If that was 20 instead of negative 20, this would have gone outwards. Right? In our case, make sure you do inwards. That's what I want to change here. And I do want to make a small comment here that I want you to play a little bit around with this, because our goal with this filter is to exclude points that are near the boundary. If you digitize, like maybe I did, if you look at my original boundary, which is the black line, there are some parts of this field, like maybe on the west side here, that my boundary is actually really far from the points. And that's because most likely I included in this boundary some grass area outside of the field. So what I do want you to think about is if you do -20 and remake the plot, take a look to see if your buffer area is perhaps touching the outer points, most of them at least, right? In my case here, I think I tried a -25. And that seemed to be, and I'm going to change this line width to 1 just to be able to see better. But if I change to -25, I come a little bit closer on the west side. Of course, that also means I'm removing more points on the east side. And, you know, perhaps the best approach would be, now that you have the U-monitor data, for you to come and do a boundary that's really close to the limits of the points. That would be the best. We're not going to do this in class, but I just want to show you how I do want you to, perhaps on your side, because we all have different boundaries, to play a little bit around with this distance here and make sure you're getting at least, you know, at least close to where the yield points are in all sides. I'm going to keep mine to 25. Again, this is going to be a place where we can all diverge a little bit. It's going to be based on your boundary that you digitized. On my side, I'll keep -25. In your side, this may be maybe a little bit more, maybe a little bit less. It's going to be up to your judgment. Okay, so now just looking at this plot, what we do want to do here is only keep the points inside the buffer, right? So we want to remove points outside because we are assuming that they have this issue, especially the issue of the picker not having the head of the picker completely full when it's reaching the ends, right? And it's turning around. So we have low yielding data points on the edges that could be attributed to that type of error, not having a full picker head, I guess, at the end of the rows. So knowing that we want to keep the points only within the buffered area and remove the ones outside, let's come here and apply this logic in this next chunk. To do that, because this is based on spatial information, it's not just, you know, if I have a column, like we don't have a column for X and Y for longitude and latitude or meters in UTM, whatever that is, we don't have that. So there's no column we can say if this column is less than this value or more than that value, keep. We don't have that option here. But we do have another option that using the fact that this is a geospatial object, we can use that to our benefit. So let's come to this chunk here. We're going to start off with the object yield 17 underscore W underscore SF. Remember that this object is the one that we applied already to it, the min max yield, min max speed. So this object yield 17 WSF already has 4 filters applied to it. That's what we want to use here. You give it a pipe, and we're going to use a function called ST underscore intersection. So this function from the SF package is going to look for the intersection between our yield points, so the points in this map, and the buffer. I guess I forgot to finish that the code here. So we want to do ST intersection and give it the buffer object. So yield 17 WSF, it is an SF object. Buffer, it is also an SF object. So we're taking the intersection of both of those. So we're overlaying and only keeping what's shared among them in this case. So if we do that, if you run this, you get a warning there. That's completely fine. You can just ignore it. And if you print this object, now we are down to 26,990 observations. So here we lost about 2,000 observations based on the previous data set, which was the speed filter. So again, we're using the function ST intersection to intersect our buffer and our yield points that have already been filtered by the speed and yield filters. In this case here, and then applying the ST intersection between the buffer and those points. Any questions here? Maybe we can take a quick moment.
How much of a difference should there be between all numbers? What you have up there, and how big of a difference between?
So if you try to if you look at your map, if you try to be close to your points on the outer boundaries, I mean, I would not expect it to be more than 1,000 difference. Yeah, 200. I was going to say less than 1,000, but if up to 1,000 is probably still. What maybe here in Athens. So what I got was 26,1990. Which one? What did you get?
27,771.
Okay, no, that's still within that. What about Renelisa? How many?
26.
Okay, so very close. Neva? Something happened?
Yeah, maybe because I got 2062.
Okay, yeah, that is not what we want. Okay, so my guess, and this is, okay, so let's do this. On your chunk, so Neva here got 62 observations. That's clearly not right. So my guess is if you just select your buffer and just print the buffer itself so we can look into it, what is the CRS of your buffer? Okay, it is the same. Okay, so because my hypothesis there was if you have so the buffer was based on the boundary, right? So if the boundary was in WGS84, it will look at this distance here, and it would take 25 degrees because it is 25 units of whatever unit that the layer is in. So if for some reason you have forgotten to transform that to UTM, then this would have been 25 degrees, which would be a lot more than 25 meters. And that's why I was asking. Yeah, so that's not the case.
I want know yield 17 WSF. How many rows it has? 17.
So on my side, I have 28,950.
Something wrong with this.
With that, okay, so if something's wrong, and this is, I think it's good for us to take a moment here to troubleshoot this because all of you, I'm sure, are going to get to a point where something happens and you're like, all right, I have no clue what's going on. So you kind of start at the error, right? So in this case here, Neva is getting 60 some rows, something is wrong. I first checked the buffer to see if the CRS was correct, and it was for her. We checked the number of rows of the data coming into this operation, which in my case is almost 29,000, and for her case is how many? Yeah, okay, so then the problem is at the level of this object. So what we do is we go back to the chunk where we created this object here. So this would be before we implemented the field boundary, right? So this is where we created that data. What could have happened? Let's see, what could have happened here? Maybe if you check this, well, maybe let's check the number of rows of the U17 WYF. I have 30,000 some. Okay, so we're kind of narrowing down here where the issue is. So it is here. I would say maybe what could have happened is check your Boolean operators. So we want more than min v and less than max v. If your Boolean operators are correct.
Wrong column.
Okay, yeah, so we want to, yeah, there you go. So if you fix that, I think you should get to a closer number. While you're doing that, just let me check. Anis, what was your, or sorry, not Anis, Sundays.
27 4.
Okay, so similar to mine. And Doug, what was yours?
26.
Okay, yeah, that's all doable. Let's check online. The students in Tifton, how many number of rows did you get on your, let's see here. So we were at the buffer. So how many data points people in Tifton got on this after applying the position filter?
27,400.
Yeah, you got around like 26.
Yeah, I'm like
Yeah.
27 200.
Okay, so all around, you know, all that is within reason here. So I wouldn't worry about any of that. Eva, you still have the issue? Okay, nice. So that's more realistic. All right, I think well, Kumar. I guess I forgot to ask you, Kumar. Sorry, Kumar and Rajamar. What numbers did you get?
I have 26,800 something.
Okay, that's okay. And Hejimar? Okay, I guess Hejimar may not be there, so let's keep moving. Okay, so we got we can look now. So I'm just looking at the summary here. I think I left you the code for this. So looking at the summary here, now I'm looking at the yield summary for the object that received the min-max yield, min-max speed, and position filter, right? So now we see that yield is ranging from 206 to 2,282, which I think is similar to maybe some of the previous steps that we were doing. But this is again our final summary of the clean yield data. All right, so next here, I just want to go ahead.
Is it okay?
Yeah.
Excuse me. Is it okay if the summary is a little bit different, like in some points?
Yeah, it's going to be a little bit different especially because of that position filter, right? And if it is a little bit different, that's okay. In this case here, we definitely don't want a very large difference, right? So yours should be around 206 and around plus or minus, let's say, I don't know, perhaps plus or minus 500 on the max side. Maybe let me ask this. Is anyone getting a very different summary from mine? Mhm.
First quantile median.
A little bit different is fine. And it's again because of that position filter being different for all of us. All right. So I do want to create some code here for us to look at these summaries again in a like a side-by-side way. So the first one that I want to do here is get the summary for the raw data. I want to assign that to this object called summary raw. So because we're talking about the raw version, we're starting with the yield 17 underscore W. That's our starting point. I want to use here the function summarize. So a quick recap, we have used the summarize in the past. Most of the time it was a combo of group by summarize, right? So we use that combo a lot already, where we do a group by a certain variable, and then we do a summarize to get mean, max, mean, whatever it is. However, the function summarize can also be used by itself. In that case, it's just going to get the summary to you of the whole data set. It's not going to create groups that give you summary for the groups, right? Because we're not using group by. So in this case, I do want a summary for the whole data set, so I can just go ahead and use the summarize function. And just to not make this confusing either, is there is a summary function. This is not pipeable, it's not tidyverse. It is a base R function that gives you a statistical summary already like that. And there is a summarize function, which is coming from the dplyr package, and we use in a pipe. So just to make that distinction here so we don't get confused. So the first thing I want to do is calculate the number of rows that were left. To do that, I want to call this column here n. So I'm going to say n equals to, and then there's a function called length. I want the length of yield in pounds per acre. And then make sure you close both of those parentheses there. So the one for length function, the one for summarize. If you come after the parentheses of the length function, add a comma. You can break code a few times because we're going to be adding multiple lines here. The next one is I want the minimum. I want to call that column min. And min is going to be equal to, there's a function that's also called min. And I want the min of yield pound per acre. So just to not get you confused again, the first thing that we say here is the name of the column, right? So n and min are the name of the columns. I could name this min like minimum, or I could name it Leo, whatever, right? That name does not matter. I'm just giving a short and useful name for us to know what it is. But the function here, min function, that is followed by a parentheses, that's the actual function that's applying, the minimum for us. So just to make that distinction. Right, after getting the minimum, I want to get the mean. So mean, which is going to be equal to a function of the same name. So mean function of yield LBAC. Add a comma, here return. After the mean, I want to get the maximum. I want to call that max. So max equals to, and then a function of the same name, max of yield LBAC. Give it a comma. The next thing I want to ask is for the standard deviation. I want to call this column SD equals to, there is a function that has the same name, SD. I wanted the SD of yield in pound per acre. And then lastly, I want to give it a comma and calculate the coefficient of variation that I want to call this column CV. There is no formula in R that does this for us. However, the formula for CV is basically, if you open and close parentheses, it's going to, and you go inside the parentheses, it's going to be standard deviation divided by mean. And here, notice that this SD and this mean are basically the columns that we're creating. These are not functions, times 100. So if you run this, and if you've got all of your closing parentheses correct, you got all of your commas correct, it should have worked. And if you printed, this is what we get. So a data set of one row and multiple columns, where each one of the columns is one of these metrics that we calculated. I do want to do a couple more things here on this pipe where I want to add. So when you close the summarize, add a pipe, I want to create a column here that says that this is the raw data, so we can identify which is the raw, which is the filtered. So I want to create a column. We just mutate for that. I want to call that column data, and I want to say equals to raw, open and close quotation marks, raw. If we do this, and we printed, you're going to realize that now at the end of the last column here, we have this, the last column, the data set, we have the data column that we just created and with the raw value. I do want to bring this column here to the beginning of the data set, so have that as the first column. There are a few ways we can do it. Let's give it a pipe. We're going to use the function select, so dplyr colon select. I want to call that column name first, so data, and then everything else. So everything else, I don't care the orders. It can be the order that they are in right now. I just want to move the data to the first position. So because I want everything else, I can use a function called everything. That's just going to include everything else and have data as the first one. So if you print it, now we have the first column here being the data, and the value under it is raw. And we see that we have total number of observations being 31,724, a minimum of 0. We're seeing here the mean, the max standard deviation, almost 36% coefficient of variation, and then we have the geometry. So this is the summary, statistical summary for our raw data. Now I want to do the same thing with the filter version. I did leave you all the code with a couple of differences. One of them is I want you to help me to determine what should be the data set coming in here. And also another difference is that the data, I'm calling this clean, whereas on the raw, we call data equals raw. So we know which one is which. So now before we run this function, if you just run as is, you can get an error because those 3 dots on the beginning of the function. So let's remove those 3 dots. And I want to ask you all, and then one of you to help me here to determine what should be the data set that we use to bring in here. If I want a summary of the filtered version. Maybe let's ask,
Like
yes, go ahead, Kumar.
yield 17 WPF. That was the last, like at the end of everything.
Yes, that's exactly it. Thanks, Kumar. Yeah, so that's the one that if you remember, the EL17 WPF was the one that we have applied already, the speed min max, yield min max, and position, right? So that's the one that we want to start off here. So if you go ahead and you run it, and then you just print that. Again, things are going to be different here because of the boundary, right? But it should not be terribly different. So we know this is the clean data. In my case here, I have 26,990 rows. My minimum is 206. My mean is 1,237. Perhaps really the one that we should all look at is CV. So you can notice how the CV here went down to 26, whereas it was almost 36 before. So 10% less coefficient of variation on the filter version. Is anyone getting a very different CV here? Like more than plus minus 5%? Okay, I don't hear anything. So I'm assuming not. All right, so just for us to better visualize this. Yes. Oh yeah, thanks, Neva. Thanks, I appreciate that. Yeah, so Neva just remembered me, and that's great because I can keep going. So maybe, let's see here. Maybe let's just go through these 2 other chunks because I think we just have to run them. There's not a lot that we're doing here. So let's just finish these 2 chunks and then we can stop here and continue next class on Friday. So here on the next chunk, I left you the code already. I'm just starting with the raw version and I'm binding rows. So when you do a bind rows, you basically have to have all the same columns across both data sets, and they have to be ordered the same way. So you can basically just take one and bind rows right below it. If they have different number of columns or different names, bind rows does not work. So if you run that, it's just gonna bind rows of these, of the raw and the clean, so we can see them side by side and compare those numbers. So really, perhaps if we focus here, you know, we decrease maybe around 4,000 rows, give or take, from the raw to the clean, or minimum increase from 0 to 206. Of course, these is, in my case, yours is going to be slightly different. The mean increased in the case of the clean, so the clean has a higher mean than the raw. Because we're removing so many of those low yielding points that we are attributing to yield monitor errors, our maximum decrease on the clean compared to the raw, almost in half. Our standard deviation decreased a lot, and because of that, our CV also decreased on the clean version. So you can really see how applying these filters is changing the distribution of your data, which is the actual data that you're going to use to, you know, look for or create management zones, create yield potential levels. So this is one of the reasons why it is so important to clean your yield data and not just use, you know, data that's coming right out of the yield monitor system. Okay, yeah, let's just finish this one last chunk here, and then I'll give some time for us to talk about the mini project. So in here, I left you part of the code. I just have one more thing that I want to ask us to develop here, which I'm showing you a geom density. So this is the statistical summary density of the yield pounds per acre of the raw data, right? So it is the raw data right there. I'm using the column yield pound per acre and just having a blue fill and 50% transparency. I do want to come here and add another density. And actually, you can just copy this. So copy just the geom density part of the code. Add a plus, hit return, and paste it. I want to change two things here. So one is the data coming in. I want to show you the density of the yield data for the clean version. So that would be the yield 17 underscore W underscore PF. And I want to have a fill of different colors. So instead of being blue, I want this to be yellow. If you run that, let me just keep this a little bit like that. So if you run that, you can now see a little bit of the comparison of how the data distribution for yield changed, right? So we can definitely see that on the raw version, on the unclean version, we have a lot more low yielding values on this distribution on the left side of the tail. That now on the clean version, on the yellow density here, we do not have as many. So we clean those. And also here on the side, even though this tail is, we cannot really tell which one of the densities have this long tail, but we do know that the maximum value for the clean version, so the yellow density here, ends at around 2,200 something. So it ends here, and the long tail is because of the raw density. So this is just a way of us visualizing the statistical distribution of this data before and after applying the filters. Okay, so we can stop here. So next class, we're gonna keep going from here. Yep. So next class, we're gonna start from here. I do wanna tell you that I am participating in a program that unfortunately meets on Fridays. It's not every Friday, but every time we meet, it is Friday mornings. So this week is going to be another one that I'm going to have a session for this program that's going to be in the morning. So I'm not going to be in person. I will, however, send you the videos of last year that for the most part should be the same. Maybe some file names, maybe a slightly different name, maybe the project names are a little bit different, but I'm sure you can figure that out as you watch them. So I just want to let you know, I will send you an email saying, here's the video, here's the script, follow it, we'll catch up with that. I mean, I do want you to watch it, you know, before the class on Monday. Again, if you don't want to watch in this 1 hour that we have on Friday, you don't have to come to class. You can watch this on your own, you know, office, home, wherever you want. However, you do need to watch it and complete the exercise before Monday, because this class is sequential. What we do today is going to impact what we do tomorrow. So if you do not watch it and you come on Monday, you're not going to be able to follow on Monday. Make sure you do go through it, you know, before the class on Monday. All right, so let's save here the project. Let me take your attendance. And then we can have 10 minutes to talk about the mini project. All right, so make sure you claim your attendance. And then if you do not have questions about the mini project or about the assignment that's due on Friday, you're good to go. If you do have questions or want to stick around to hear what others have to ask, you know, we have 10 minutes for that. All right,
Okay. I'll begin with one thing. Is there any way we can extend the deadline for Friday, like by a couple of days?
so that is something, if you have, like, if something unplanned came up, email me, we can talk about that on a one-to-one basis, but I would not extend for everyone without a reason. But we can talk about it if something came up and then you need some extra time. So feel free to email me or, you know, we can talk about it.
Okay.
No, so Renelisa's question was if I am particular with the unit of measure. I mean, I'm not, as long as you're consistent, like you're always using the same unit throughout, then I'm okay.
So I had a question about the interactive map.
Mhm.
So the county names, do they need to be on top of the county where you can read it by looking at the map, or just have it where if you click the map, it will tell you?
So on the, I'm trying to think about it, because I remember that we added the county names on the static map. I will have to go back to our class exercise and see. I don't remember now if in class we added the names on the interactive one.
I don't either, and I'm not sure how
Yeah.
to do that.
Because if we did not do in class, then I wouldn't ask you to do it in the mini project. Let me see. So that was, we can check here on the NAS project. Let's see here. So I'm just pulling up the NAS project. And I want to launch that script. And I just want to look at the plot. Yeah, so in class, we did not add the names on the interactive map, so you don't have to do that. But you do need to do that on the static one. All right, any other questions about the mini project or about the assignment that's due on Friday on data, open source data?
I have another one on, okay.
Kumar, sorry, can you just hold up 1 sec? We had Neva you're asking a question, but I'll get right back to you. Yes, Neva.
So, same, when we're doing our extracting that map, it's fine. The same map is fine in HTML.
Okay.
As we are doing, as we are saving the HTML, so right now we are focusing on that map should be good in HTML, but it's not good in R, or if you want to extract that and you want to use it.
So is that a specific map you're talking about, or is like everything?
For FLNet, the last one where we have the 3 maps all together.
Okay, oh, so, okay, so you're talking about the assignment? Okay, just yeah, I thought you were talking about the mini project. Okay, so Neva is asking about the assignment, the last set of maps that we put together using Patchwork. That one is not looking nice, is that what you're saying?
Yes, when I'm extracting for, R, I mean,
Mm-hmm.
yeah, if I see it in the plot, it's fine.
Yeah.
But, you
When you're rendering.
rendering
Mhm.
and see HTML.
Okay, perfect. So let's get to that. So just to, while I'm getting to that here on my side, just to repeat to those online. So Neva is saying that on the assignment that's due on Friday, when she renders the into HTML, since you are all sending me the HTML, the map does not look nice on the HTML. So she's asking how to fix that. I do want to show here. I don't remember now if I talked about this in this class, and I guess independently of that. So whenever you're combining them, when we are exporting to file, we can change the dimensions on DigiSave, right? But if you're not, so if you're rendering and the dimensions are not correct, we can change a chunk option. So if you come here in your chunk, we can assess chunk options by typing hashtag vertical pipe. And then there is an argument for figure width that you can give a number. So let's say on my case, it could be 12. It could be the same dimensions as the DigiSave. So fig width 12 and fig height 8 would force this chunk to create a figure of these dimensions when you render. So maybe try that and see if that helps when you render. I think it should help. Yeah, so that would be the fix for this.
Hey, Dr. Vassos, I have like a issue that looks like this. Vinicius Chipton here. But like my problem is being with legend of all the plots that I did. The first plot with my soil type, there's like 8 soil types, and like the legend keeps on front of the plot every time. I did like I tried to change the map and try to change everything, and I couldn't. I even played with the size and doesn't work. Do you think like do that way you show it now would works?
I think if you change, because really, so whenever that happens and we want to see the, like how your map looks when you export it, then we change those on here on the width and height of DigiSave, and that's how we can play around with that a little bit. But because you're all rendering, I think that if you change those settings here on the chunk level, that would be the fix. So maybe try that as well, and Eva, you as well. And I mean, everyone else, if you're having issues with the map not looking nice when you render, I think these two arguments here are going to help you with that. Yeah. And Kumar, sorry, I did not forget about you. Do you want to go ahead and ask your
Yeah.
question?
Yeah. So my question is, I'm not sure how do I pick like area to do the assignment work. Can you suggest me if I do not have already chosen one, how can I randomly go and pick one?
So do you have any do you have field trials in your research?
Not yet. I mean, I've started this semester and I've not reached to that part, I guess. That's why I do not have.
Does your advisor normally conduct field trials?
Yeah, he is supposed to, but we have not discussed it yet
So
for my project.
the idea here is that you would use an area that either you are using or is of interest to you, or an area, in your case, I guess, since you don't have anything yet, an area that maybe your advisor has used in the past.
Yeah.
So maybe, I mean, well, that would be the ideal scenario, but it is due in 2 days. So, you know, for the sake of you having time to actually do the exercise and not spend a lot of time trying to get a boundary from your advisor or a centroid, I'm gonna send you a centroid. And then, so what crop do you work with?
Tough grass.
Okay, turf grass. Okay, sounds great. I'll see if I can find something. Well, I'll send you a centroid of a field that
Okay.
has grass at least. May not be turf grass, but at least it is grass.
Okay.
I'll send you that after class.
Okay. Yeah. Thank you.
All right. Yeah, no problem. Well, I guess let me ask this, does anyone else in the class work with turf grass that you could have a field to, a centroid to share with Kumar? All right. maybe not, Kumar. I'll send you one of a field that at least is grass, so you can use for that.
Okay.
All right, any other questions?
I did like everything here, but still not working. Like my legends keep in front of the plot. There's something else that I can make the legend smaller. I already like find out how to like split the legend and make that horizontal on the bottle, but like still like so big, it's huge, it's a huge legend. It took like half of the plot of my
Okay.
soil type.
Yeah. So even if you increase like the height and width, it doesn't fix that?
Isn't fixed.
Hmm.
I can
Okay.
create like each on the GitHub to show like what is going on. Maybe it helps. But like now it's not working at all.
Yeah,
Even
maybe-
when I try to move like the legends on the ggplot code. And, like I do bottle, maybe they go and I like try to write and they don't go. I don't know, maybe I'm doing something wrong.
Okay, so maybe if you can, yeah, open an issue and show me a screenshot of what's going on, I may be able to help. And if not, I don't want you all, because since we're all using different fields, maybe some of you have this issue, maybe others don't. So if we cannot find a solution, maybe I'll ask you to submit that figure that you export through DigiSave, along with your HTML, right? So even though in the HTML is going to look bad, but you can send also the PNG for that.
Sounds good.
All right.
Thank you.
Yeah, absolutely. Any other questions? I guess not, so we'll wrap up here. Thanks, everyone. And again, we're not gonna meet in person on Friday, but I'll send you an email with instructions for how to follow the exercise. All right, see you sometime.